Good afternoon, and thank you for attending this session. This is the last session of the day. Okay, my name is Nirmal Mandal. I am from Central of Railway Engineering, Central Queensland University, Australia. Today, I will be talking on joint bar of insulated rail joint. This is one important piece of insulated rail joint, and okay, this is the layout of my talk. I can start with some background knowledge and what are the problems this type of joint is facing in real life, and then some theoretical aspect of the analysis and the finite element modeling, and finally some result discussion and ends up with conclusions. So in terms of background knowledge, these are some key points relating to insulated rail joint. And key points are, you can see, obviously this is the key component of the joint. And you can see important aspect is the rigidity. Why rigidity is different, I will discuss with the photo in the next slide. And the height mismatch, our second speaker talked on that thing. And finally, we can discuss something signaling issue relating to this type of joint. So these are the key points in terms of background I discuss with the help of this joint. You can see these are the photos of four joint you can see. So this is the one rail piece, another one rail piece, rail 1 and rail 2. These are connected. So this is the end of the rail 1, 2, and connected by joint bar. So one joint bar this side, another joint bar on the other side. It is connected by the bolts. Bolt can be 4 bolts, bolt can be 6 bolts, or different bolts. And you can see the separation from one joint to another joint by end post, because this is for isolation. Isolating this section to another section, it is called signaling block. This signaling block is useful for signaling people in the control room, and they can identify where is the train moving. So if train is here, that block is red, and another train cannot come into the block. So that's why the history of signaling block. Now you can see, so why it is important? Why this bar is important? You can see this is the end of the rail, and the bending rigidity of this joint at the gap is finished. There is no joint, no rigidity. So to cover that rigidity, to back up, the joint bars are used. So how much they can cover? Is 2/3 of the bending rigidity of the continuous rail is covered by joint bar. So that's why this piece, the connection rail joint, considered to be one of the weakest link in this track. So now in terms of problem, what are the problems we are facing? So in Australia or elsewhere, what are the problems relating to this joint? You can see that this is the Australian experience. You can see this is the end post, and this is the rail 1 and rail 2. Because of the dynamic load, you can see this is the 8 millimeter end post. You can see because of the plastifications and plastic flow, you can see the thickness of this end post is gradually reducing. What happens if the one rail touches another rail? That means signaling block fails. That means this is the controlling problem, the destroying of electrical signal. Because of severe plastic deformation, you can see this is the seeping out as the material is going out. So this is not the good thing, so it should be avoided. So that is the joint from the track, and this is the failure of the rail, and you can see away from this rail head, some other stuff is also important. Not so popular in Australia, but elsewhere in USA, Canada, it is another common factor of failure, mode of failure. You can see this is the crack of the joint bar. You can see this is the bolt hole crack. So this is important. Compared to this one is less, but it is there. And if this type of failure happens, this one, catastrophic failure of the whole thing can happen is the huge loss in terms of goods, loss of in terms of life. So we have to address this type of thing. Yes, this research is from Australia. So far, we targeted this area, and I produced a couple of papers, journal papers on that thing. Now I thought that we should do something, say, away from this railhead. What is happening to other parts? So that's why my talk is relating to the joint bar. It is away from the top crown surface, and now it's focusing on here. That is the little bit history. Okay, so you can see the USA, this is the experience of failure. This is the joint bar failure. You can see this is the top of the joint bar. It's called fish fillet there. So you can see this is the crack initiation and the failure, fracture. In the foot, you can see this is the crack initiation and it is failure. So it is important to address that thing. So I started my study on that joint bar. Because why it is happening and how it is accelerating one after another, one cycle after another. You can see because of this mismatch and height mismatch and the gap between two rails, the second author discussed about that thing, dynamic force. That is the P1, P2 forces. These are the thing happening. And P1 force is responsible to, say, rail top battering. And the P2 force is responsible for track damage. And because of this thing, bolt looseness is happening. As a result, severe, more, say, deflection is happening. And hence, it accelerates the P1, P2 force, the dynamic force. So this is the cycle is happening. As a result, bolt hole cracks, broken bars, the rail bolt bends. These are the things happening. So this is the problem important, and we have to notice that thing. So little bit theoretical stuff there, and this is the study based on beam on elastic foundation. This is the fourth order differential equation. By integrating, we can get the deformation pattern. And from deformation pattern, if we differentiate twice, we can get the moment distribution. So this is the moment distribution of the rail. So our talk is on joint bar. So how this moment distribution can be transferred, formulated to the joint bar. So that is the thing can be done by another factor, which is called joint efficiency. Joint efficiency factor. If we multiply it by this factor, with this, the moment distribution in rail, we can get the moment distribution of the joint bar or fish fillet. So this factor in the literature it is established by Jenkins, and this is the 60% to 80%. So I analytically calculated this value, the joint efficiency, using the Australian standard 1085, 2002, and I calculated this thing is as nearly 60%, but this is so close it can be comparable. So this is the benchmarking analytically with the established value in the literature. Now, little bit on finite element analysis. So this is the solid modeling part here. So this is the end post, and this is the joint bar, fish fillet with 6 bolts, 3 bolts on side, 3 bolts on other side. And from here, this is the solid part is 2.4 meter long. And there will be beam model. You can see a little bit there. The beam model there, beam model is connected there. So all together is 12 meter long. So why 12 meters? Because if we put load here, like load here, then say like 6 degrees of freedom can be nullified, can be 0, far away from the applied load. How far? So from here, we calculate that it is 6 meters from there, 6 meters from there. So that's how we got 12 meter long. So this type of length of the piece can be seen in real life, and shorter length is also possible. Look, so if a load is there, so this is the insulated rail joint, and this is the bonded joint. So if load is here, load is there, how it is applied? So like it is through the bolt coming to the joint bar and coming back to the rail. So if load is here, wheel load, so it is supported by this bolt, with this way. So I can focus on this area. So this bolt load here, what is happening to the middle side? So very quickly, I want to present some result by, so this is the result from the contour output and using path analysis. So I defined a path. Path is like this. So this is the center bolt close to the end post. This is another bolt close to the end for other side. So I selected a path like this, which I called horizontal path. And this is through the rail, and I define another path from here to here. This is called vertical path, path number 2. So on that thing, I put the deformation behavior. So you can see this is the U2 is the vertical deformation from the middle point, from this point and from this point. We can see. So this point is denoted by this color. It is higher than the deflection at here. And if we go from this point to this point, we can see this point is 0.6 millimeter, and it is more than that. So it is deflected here more. That means this form arc is the bending. So if we see what is happening from top to bottom, and we can see, you can see it is nearly this value, and it is similar all the way from here to here. What is happening to U3? U3 is longitudinal. You can see U3 is from here to here is nearly 0. What does it mean? That means this is the neutral axis, and it is not deformed. So away from displacement, if we go to the stress side, what is happening? The stress value here and through this line and so on. We can say I put two stress components. One is the vertical stress, so S22, another is the von Mises stress. So we can see, so in this point over this time period, 4 seconds, so it is same all over. If we see what is going on from here to here, so we can see it is going there. So in the middle, you can see this is not so much important. You can see this is the S331 example. So the value is somewhere here, which is 0. What does it mean? So you can see the maximum longitudinal stress, say it will be in compression here, it will be in tension here. That means somewhere it will be 0. This is the position of neutral axis. So I applied that the load in the form of pressure, and which is yield point 780. Then we saw the stress is somewhere for 300. So it is elastic. So that is the elastic theory for calculating the fatigue life, and this is the linear rules. So you can see why it is linear rules and where is the location. You can see this is the infinite life 10 to the power 6. If we put this rule, it will be somewhere in high cycle fatigue, and this somewhere it is low cycle fatigue, and lower than 300 cycle is the receding life. So we are talking about this thing, but what is happening to the close to this surface? You can see this is the result. This is the elastic thing, and you can see that somewhere 8 millimeter and 12 millimeter, there is no plastic thing after that, so it is elastic. Definitely in the joint area, it is elastic behavior, so Minard's rule is important. Thank you very much for your attention.